Right.
All right.
Thank you very much for that introduction, Chair. Just one correction. I'm no longer the Director of the Centre for Materials Engineering at UCT, although I'm still a member of that centre. I'm now the Director of the Electron Microscope Unit at UCT.
Oh,
thank you also, Leslie, for that presentation. I think it set the scene very well. My talk is going to focus more on people than on the materials, and I think you'll see why as the presentation progresses. I've titled it Physical Metallurgy Requirements to Maintain Baseload Energy, which is a very topical issue, particularly in South Africa at the moment, and of course through the rest of Africa as well. It's subtitled, How Do We See the Forest for the Trees? And I'm hoping that that theme might come through as we go. So I just want to take a step back. I'm not sure even if Leslie remembers this actually, but I started my PhD out at the time that South Africa was full on in the throes of developing a new steel, which was called, or is still called, 3CR12. And in fact, the same year I started my PhD was the year that they had their inaugural international conference in Johannesburg on 3CR12. And 3CR12 was all about this dual phase ferrite martensite steel, which in the picture on the right, transmission electron microscope micrograph shows that there's a very, very high dislocation density that occurs in the ferrite immediately adjacent to the martensite. And that, of course, produced a whole lot of mobile dislocations, which gave the steel superb ductility. Now, the reason I'm mentioning this particular steel and its birth, which happened in the late 70s and into the 80s, is that it came about as a result of a very well coordinated effort, which was driven by what was then called Middelburg Steel and Alloys in Mpumalanga, and is now called Columbus Stainless. And so important was this steel development, and so big was it at the time, that they even named a ocean-going yacht after it. You can just see the 3CR12 there as a label on the yacht, and this was in 1985 when it competed in I think it was the Cape to Rio race at the time. But what was happening then was that there was this coordinated effort, as I say, driven by the company, but involving University of Pretoria, Mintech, CSIR, University of Cape Town, and the University of Witwatersrand. Now, they were the main contributors to this conference. There were many other universities that also played a role. And what happened is that there were annual meetings which continued for some 8 to 10 years afterwards, produced many graduates educated in stainless steel, and probably most importantly, popularized physical metallurgy at research level in South Africa. This was something where people really pulled together. And Leslie mentioned, you can talk about networking and collaborations, but they need to be meaningful. And this was one such happening some good few decades ago that actually pulled a lot of people together with very, very meaningful and engaging research and output, which, as I say, was driven by the company. So returning to the context of my talk then, why is physical metallurgy important for base load energy? I'll come back to that slide on 3CR12 a little bit later. So, of course, in a power plant, you've got very complex service conditions, high temperature, 500 to 600 in the main steam pipes, of course, much higher in the boiler area, and you've got steam operating at fairly high pressures. So a very demanding environment. Now, once again, if we take a step back and if we use coining this once again, a very old term, which happened before Windows came along, which was WYSIWYG, what you see is what you get. If we had a situation where you had a material, and this is a polycrystalline metal of some sort, and you measured its mechanical properties quasi-statically, and you obtained the tensile yield, etc. And if that material were then operating in an inert, static service environment, where the service environment is ambient, then you are going to have stable properties, in other words, time independent, and the component should last forever. Of course, what happens under non-static conditions, in other words, elevated temperature, as you would get in a power plant? Well, microstructure can change as a result of atomic diffusivity, increasing with surface exposure, and of course, it can be stress assisted. Now, this driving force for change is due to the fact that the metal, in this case, steel, is deployed in the initial non-equilibrium condition. And therefore, if you give it enough exposure to an environment where diffusion can occur, stress can assist those microstructural changes, the microstructural state and mechanical properties, of course, become time dependent. And the situation gets a lot more complicated. So if we take the creep strength enhanced ferritic steel, which is used extensively in steam pipe in a coal-fired power plant, it's deployed in the tempered martensitic condition. And the reason for doing that, of course, is that in the fully martensitic state, it has very high strength, but very low ductility and toughness. So it's then tempered to restore some good ductility and toughness. And of course, moderate strength is key, because strength at the end of the day to sustain the high pressures and high temperature is critically important. But of course, this is still a non-equilibrium state. So although we've taken a fully non-equilibrium or highly non-equilibrium martensitic condition, and we moved it somewhat towards equilibrium by tempering it, it's still a non-equilibrium state. In that state, it has a number of different components in the microstructure, which of course lead to strengthening. And over time, the microstructure, as it moves towards equilibrium, of course, we get other phases forming, namely Z phase, Laves phase, coarsening of the M23C6 carbides, dissolution of the very key strengthening MX precipitates, and we get microstructural change. With the result that we need to measure what the expected lifetime is of these steels, because they are going to change in service. So, of course, we evaluate the time-dependent deformation, which of course is creep, and we do that quite conventionally by mostly performing uniaxial tensile tests at temperature, under constant load, constant stress, and we generate a strain versus time diagram, which of course shows different stages of creep and eventual failure. And we can do that for many different tests for many thousands of hours. We can eventually determine an applied stress versus time to rupture. Therefore, if you want your plant to last, say, 100,000 hours, you know the stress limits that you should be testing or exposing your materials at in service to ensure that you don't get failure before end of life. Now, that all works very well if we have a situation where we can clearly predict performance. So this is a very simple graph, once again indicating an arbitrary microstructure parameter on the y-axis versus service or exposure time on the x-axis. And if we take a material in a known and standard initial state, as we would expect if we deploy a quench and tempered material known condition, then that material's microstructure will change over time, and eventually, of course, it will reach an end of life. But because we measured that, we of course get an end-of-life prediction, and we can then work out safe operation. And all is fine and great, and perhaps there's no need for further analysis because we know everything, and everything is going to work according to plan. But of course, that's not the case. What happens if the material is deployed in an initial state, which does not perhaps represent the expected quench and fully tempered or appropriately tempered condition rather than fully tempered? In other words, a property that we can then predict its life. If that doesn't happen, then of course, and we don't know that that hasn't happened, it of course gives rise to this, what we know as metallurgical risk. So I always teach my students that mild steel is so popular in engineering because in fact there's very little metallurgical risk associated with it. You can do anything to mild steel and it almost always behaves the same way. It's so easily weldable, very little change in the properties across the weld, and consequently what you see is what you get. But that's not the case with very complex materials used at high temperature and high stress. So if we then consider this metallurgical variability, instead of having this black line at the bottom, which is predicted behavior, we'll start with a condition which is only subtly different in the initial state. In fact, the difference might be so subtle that we don't actually pick it up in a quality control assessment when we measure the time-independent properties. But in service, that microstructure might now change quite differently to what might be expected because of the subtle difference in the initial state. And that may well become exaggerated. The difference between these curves gets greater and greater with time. And as a result, this enhanced difference as aging increases leads to accelerated damage or early failure. So that is the complexity of what can happen to these rather sophisticated materials used in power plants. So there are, of course, many different reasons as to why unpredictable performance can arise, not only perhaps simply in different starting state of the material. There are process excursions, for example, the temperature, stress, and corrosion environment could differ over periods of time in service. We could have poor fabrication, for example, welding and post-weld treatment, which may well be unknown and therefore unpredictable feature. And of course, there could also be poor inspection analysis where we think something is good, but it's not good. So what do we need to address these issues? Well, I'm proposing that what we need is a strong cohort of physical metallurgists with advanced knowledge in steel performance and metallurgy. Now, once again, that sounds very old-fashioned, because if you look at Leslie's list of what we need to do for Africa, it's very much state-of-the-art, cutting-edge stuff, whereas physical metallurgists working on steels have been around for decades and decades. But clearly, what we have at the moment is not good enough. Otherwise, our lights would not be going out. So what does the current landscape look like? Well, engineers in the power plant industry, of course, require considerable interdisciplinary skills. I'm returning now to the people situation. For example, mechanical engineers often cover routine materials issues and overlap with materials engineers. But this is often done at a fairly low level in terms of intensity or indeed expertise. Engineers at power stations are also very often project managers. In other words, identified problems are often transferred and follow-through is often lacking. And there's limited on-the-job training because of demands at the coalface. Now, particularly in South Africa, the demands in terms of keeping a power plant running is so huge that there's actually very little time to train properly young engineers. So we have this scenario. We have young, early career engineers with limited experience, relatively fresh out of university, perhaps first job, And at the extreme end, we have highly experienced engineers who have been in the game for a lifetime career. At the moment, this cohort is very small. In fact, it's tiny. Even at the incoming end, the resources are under-resourced because of problems related to overemployment in other areas within the business. But more importantly, there is this huge missing middle. Now, of course, what happens is that these young early career engineers, they get enough training over a few years in the power industry, and then they move on because there are other more sexy, better paying, more career job prospects. And of course, at the other end, there is retirement, which in cases right now is imminent. And we're going to lose this highly experienced engineers with having a missing middle. Where does that leave us at the left-hand side of this diagram? So how does this come about? Well, one of the problems is that progression or promotion in the workplace is slow. And that's why alternative job prospects for these young engineers is very attractive. And secondly, we have a situation where we mostly have managers or engineers being active as managers rather than as practitioners. And I want to try and get to the bottom of why this is the case. What we actually need to do is to have a pull that is much stronger than short-term goals. Now, going back to, can we learn from this 3CR12 success story? So at that stage, Middelburg Steel and Alloys in the late 70s decided to throw a lot of energy at developing a new product. They took a very, very high risk. They threw a lot of money at it by supporting pioneering research at the various universities and institutions in order to be able to push this, or from their side, pull it as far as they could. They had a long-term goal, which was the development of a new product. So there are, of course, three main entities that are responsible or should be responsible for changing the situation in the base load energy supply situation currently, particularly in South Africa. They are the workplace. Okay, and of course, everybody knows that the main workplace in South Africa is Eskom. There are the higher education institutions, and of course, there is government, and in particular, the Department of Science and Innovation, and of course, the National Research Foundation. Well, how should this work? Well, in the workplace, what we should really have is teams with critical mass, even if this means extra cost. And this is a very key issue because you've got to spend money in order to create sustainability. The problem is that it's currently looked at, the company's not running well. How do we be lean? Well, we don't employ people. But of course, the price you pay them is you don't have this critical mass to be able to keep the company going. Specialist engineers must be encouraged to be involved in development research, even to the point where some activities are purely exploratory. Now, the situation here is that you need to keep those young engineers interested all the time. You cannot actually have a situation where they can be distracted into other activities. They need to be embedded in their job. And the only way to do that is to make sure that they are goal-oriented. In other words, we're looking for not just solving problems. Problems mustn't only be managed, but the goal must be improvement. Interaction, collaboration, and exposure, in other words, presentation of work at local and international meetings, must be encouraged. These people must be able to interact not only locally in South Africa, but they must be able to interact with the rest of the world. And the career track must be favorable. Now, I must acknowledge that this comes at cost. But if you don't have that, you're going to have that missing middle, and it's going to get worse and worse. Higher education institutions, of course, cooperatives must be promoted to work with industry. Just like Middelburg Steel and Alloys, they're actually forced a 2-day conference, mini conference every year. They got these people together and they put them in a room and they made them talk together. There are no quick fixes. This is always a long haul, and we have to work together. And then lastly, government. It's critical to focus on manufacturing. Yes, that's very important. That's where you ultimately make your money. And once again, Leslie showed that graph of beneficiation. At the end of the day, the more you beneficiate your materials, the more money you're going to make. But no energy equals no manufacturing. I mean, we all know that very well. Now, this last little sentence is a little bit of a stab, but it doesn't mean to say we mustn't work on nanomaterials or new materials, or we mustn't be worried about publications. But the point is, it's not all about that. And at the moment, my sense is that we've somewhat lost focus on what we really need to do in order to keep the wheels turning. So, last comment. This is the last slide, Chair. At the moment, there is, as we speak, there is a conference happening in Edinburgh called the European CREEP Collaborative Committee Conference on Creep and Fracture. Today is the last day of that event. The conference focuses on high temperature, high stress performance of materials in power plants, typically coal-fired and nuclear power plant, chemical process plant, and of course combustion engines and other things that work at high temperature and high pressure. The disturbing fact is that there's only one presenting delegate from Africa at the conference. Now, who has got the problem where the lights don't burn? I think that we can see the forest, but we really have to take a leap. And although we are throwing a lot of energy and money at developing new materials, etc., we have to also consider looking after what we've got. And some of this goes back to basic fundamental knowledge. But how do we keep that alive? How do we make it interesting, exciting? And this is where we have to work with people, we have to ensure that industries and universities work together with a common theme to try and at least keep the base load of physical metallurgists healthy, growing in Africa. Thank you, Chair.
Thank you very much for an insightful